Hey everyone, welcome back to The Explainer. So today we are tackling what honestly feels like a magic trick in the plastics manufacturing world. We're going to dive deep into literally the ultimate cost optimization tool out there. I mean, think about it for a second. If a manufacturer told you they just slashed their product costs by like 20 to 30% without dropping quality, what's your first thought? Did they secretly swap the polymer? Did they find some highly guarded secret formula? Nope. The reality is, it's not a secret at all. It all boils down to mastering filler master batches. But, and this is a massive but, if you mess up the filler selection or the dosage, your product turns incredibly brittle, impact strength falls off a cliff, and, well, you're going to be drowning in customer complaints. So we really need to understand the science here. Here's our roadmap for today. We're going to hit Masterbatch basics, dig into calcium carbonate and talc, look at the science of loading, explore professional formulation, and finally troubleshoot some real-world factory floor problems. Let's get right into it. All right, Section 1, Masterbatch basics and benefits. First things first, we've got to stop looking at fillers as just cheap additives. A filler masterbatch isn't just some random dust you throw into a mixer. It's actually a highly concentrated, meticulously engineered compound. It's got three main parts. You have the mineral filler itself, a polymer carrier to transport it, and specific processing additives. So yeah, it's a pretty sophisticated piece of engineering. And because it's engineered this way, it does way more than just save you money. A good masterbatch actively levels up your product. We're talking improved dimensional stability and noticeably increased stiffness. It actually makes the whole process smoother, gives you a much better surface finish, and sometimes it can even reduce your cycle time. So you're literally producing more products, faster. It's a total win-win. Moving on to Section 2, calcium carbonate. Let's talk about a specific, incredibly popular mineral. You'll often hear calcium carbonate called the king of fillers in the industry. It's everywhere, mostly because it's cheap, super easy to get, and great for stiffness. But here is the major trade-off: particle size. You know, if you go with coarse particles to save a few pennies, you'll end up with a really rough surface and weak plastic, like the kind of plastic that just shatters the second you drop it. On the flip side, fine particles give you this beautiful surface finish and great dispersion, even if it costs a little bit more. Seriously, saving pennies on coarse particles can completely tank your product. And the choices don't stop there. We also have to talk about coating, specifically treating the calcium carbonate with stearic acid. When you use a coated grade, you get way better compatibility with the polymer, excellent dispersion, and, crucially, much lower moisture pickup. Uncoated, sure, it's cheaper, but you are asking for dispersion issues and massive processing headaches. Understanding why you absolutely need a coated grade is how you avoid total moisture nightmares on the factory floor. All right, Section 3, Talc Masterbatch applications. Let's check out the other big player here. Talc is actually fascinating. It has this unique plate-like physical structure, which forces the polymer to behave completely differently than it does with calcium carbonate. Talc brings serious stiffness to the table, plus excellent heat resistance and really low shrinkage. This is why it's absolutely perfect for stuff like under-the-hood automotive parts or appliances that get really hot. But, huge red flag here, if you use too much of it, you will completely ruin the impact strength. The plastic becomes disastrously brittle. Which brings us right to Section 4, the science of filler loading. This is really the climax of formulation, figuring out exactly how much filler is actually safe to add. Because the number one question R&D engineers ask is, well, how much should I add? And the answer? It depends entirely on the application. Let's look at a few examples. Say you're making a thin carry bag. Your filler level has to be super low because you absolutely need flexibility. But what if you're making a bucket? You can bump that up to a medium level, finding that sweet spot between cost and stiffness. Now, if you're making a plastic chair or furniture, you can push the filler way higher because you need that rigidity, though at that point, impact testing becomes 100% mandatory. The application always dictates the dose. So, if you take nothing else away, remember this golden rule of filler loading. The benefit is obvious. More filler means lower cost and higher stiffness. But the danger, as that filler goes up, your impact strength can just plummet. It's a direct, undeniable trade-off between chasing those cost savings and risking the structural integrity of your product. Let's pivot to Section 5, formulation and industry thinking. I want you to step into the shoes of a pro R&D engineer for a second. Imagine a client says to you, hey, I want to manufacture a plastic chair. An amateur might just guess a random filler percentage to make it cheap, but at pro, they use a strict 4-step mental checklist. Step 1, What's the application? Is it going indoor or outdoor? Step 2, what are the exact mechanical requirements? Step 3, how are we processing this? Injection molding or extrusion? And only then, step 4, calculate the safe dosage limits. It is never just about guessing a percentage, it is a highly analytical process. And honestly, when you ignore that process, disasters happen. These are the classic amateur mistakes that lead to absolute product failures. Things like increasing filler purely to hit a price target without even thinking about the physics, skipping mandatory testing just to save time, completely ignoring moisture content, using uncoated filler when the process desperately needs coated just because they didn't know the difference. And the biggest one, creating a formulation without truly understanding what the customer is actually going to do with the end product. Which leads us to Section 6, Processing Problems and Mistakes. Let's take a walk onto the factory floor and see what happens when those formulation rules are broken. Let's do some rapid-fire troubleshooting. Basically, every physical defect on the line traces straight back to an R&D choice. Got poor dispersion? You probably have the wrong screw design or just bad mixing. Seeing surface roughness? Your filler particle size is way too large. Having flow problems in the machine? You added too much filler. And if your final product is super brittle, you've simply overfilled the polymer matrix. Every single defect tells the story of a formulation error. But don't worry, we do have a toolkit to fix these issues. From day one, you absolutely must ensure you're selecting the correct particle size. Always use a high-quality polymer carrier. Take the time to properly optimize your processing machine parameters. And most importantly, maintain a scientifically sound formulation balance. Really, this whole explainer boils down to one foundational idea. A good R&D engineer never says, just stuff in as much filler as possible. Their actual mantra is maximum performance with minimum cost. That's it. That is the core of professional formulation. We use fillers for intelligent design, not just to pump out the cheapest, flimsiest products possible. And that wraps up today's deep dive. You now understand exactly how fillers are used to strategically design plastic products. Up next in our Explainer series, we are unlocking the secrets of polymer additives. We'll be getting into internal and external lubricants, compatibilizers, and the crazy science behind coupling agents. I mean, if mastering fillers can cut costs by 30% without losing quality, just imagine what mastering chemical additives can do to the actual molecular structure. So what do you think? Keep learning, stay curious, and I'll see you in the next Explainer.
Before we conclude this session, I would like to highlight one important point. Many people believe that filler masterbatch is only used to reduce the cost of plastic product. However, in the real plastic industry, filler masterbatch is a much more than a cost-saving solution. It is a carefully engineered material that directly influences processing performance, mechanical properties, product quality, and overall manufacturing efficiency. The selection of the right filler is the first step toward a successful formulation. Calcium carbonate is widely used to provide excellent cost optimization, improve toughness, and enhance dimensional stability in many plastic applications. Talc, on the other hand, offer high rigid, better heat resistance, and improved dimensional accuracy, making it suitable for applications that require higher performance. Understanding where and how to use each filler is one of the most important skills for any formulation engineer. However, selecting the filler is only the beginning. Particle size, particle shape, surface treatment, moisture content, and capability with the base polymer all play a critical role in determining the final performance of the master batch. Even a high-quality filler can produce poor results if dispersion is not properly controlled or if the processing conditions are not optimized. In industrial production, engineers must carefully balance filler loading with the product performance. Increasing filler content may reduce raw material cost, but excessive loading can lead to brittlance, lower impact strength, poor surface finish, flow problem reduced, Weld line strength is the customer complaint. The goal is not simple to use more filler. It is to achieve the best balance between cost, quality and performance. A successful filler master batch formation also depends on the selecting the right carrier resin, choosing effective processing aids and lubricant, using suitable coupling agent when required, and maintaining constant extrusion parameters such as the temperature profile, screw design and screw speed. Every stage of the process contributes to produce a master batch with excellent dispersion, stable processing and constant quality. This is actually how formulation is approached in real manufacturing industry. Engineers do not rely on fixed recipe. Instead, they evaluate customer requirement, application condition, processing methods, performance expectation and the commercial target before developing the final formation. This scientific and systematic approach is what separates a laboratory trial from a successful commercial product. My objective through this channel is not only to explain theoretical concept but also the share practical industry knowledge that professionals use every day in quality control, production, product development and research and development. Whether you are a student, a fresher, graduate, a production engineer, a quality professional or R&D engineer, I hope this technical session help you build strong knowledge and develop industry ready skills. If you found this video informative, please support the channel by liking the video, sharing it with your colleagues and friends, and subscribe for more technical content on Masterbatch technology, polymer compounding, color matching, additive troubleshooting, quality control and real industrial case study. Thank you very so much for watching. I look forward to meeting in your the next technical session with another practical topic from the plastic and polymer industry. Until then, keep learning, keep experimenting and keep improving.